Okay, so welcome to today. I'm going to go over the Spring 2020 final exam. So I'll just go over all the questions and work through like the answers. All right, first question. And as a reference, the template to all the questions are also on my website. If you want to like fill in along while we go through. All right, question one. Consider the vector field and this path given by a unit circle in the plane oriented clockwise. What is the work done by F along the path? So we have a vector field, something exists, and a path is our unit circle in the plane, and they're telling us that it's oriented counterclockwise. So like this way. And question A is what is work? What is work defined as? Well, work, you could write it as, depending on how you write your notation, I usually write it as integral f dot dr. And when I see that I have this like 2D circle, I'm thinking maybe I should use something like Green's theorem. Because sure, I could parameterize this circle, and then what I would do, like I could parameterize the circle to some path, and I could say that the integral is equal to f with the parameterization plugged in, dot the derivative of it, dt. Like that's one method that I could do. But that would take a long time. I don't want to do that. So instead, I'm going to use Green's theorem. So what does Green's theorem say? It says that the integral of m dx and dy, where I'm calling my field being components of m and n. All right, it says that m dx plus n dy equals the double integral of the second component with respect to x minus the first component with respect to y, dx dy. Okay, so if we take the partial of this thing with respect to x, we get 1 minus the partial of this thing with respect to y is 2y, dx dy. Okay, so I could keep things in Cartesian coordinates and try to get the double bounds for this circle. But if I have a circle, why not just convert to polar coordinates? So I'm going to convert to polar coordinates. If you want to keep in Cartesian, that also works. You should get the same answer. But I'm going to convert to polar because the bounds will be nicer to like use. All right, so I have to convert everything in the integrand to polar coordinates. So in polar coordinates, what are the conversions? X is r cosine theta, y is r sine theta, right? So in my integrand, I have 1 minus 2. Y is r sine theta. That's my integrand. Then my differential also becomes r dr d theta. And you want to be careful that this is all in parentheses, remember, so that the r distributes. All right, what are our bounds? R goes from 0 to the whatever the radius of the circle is. Our circle is a unit circle, so it goes to 1. And we have no restrictions, so theta goes from 0 to 2 pi. Okay, so if I continue this integration, let me distribute that r out. So I have r minus 2r squared sine theta dr d theta. I integrate with respect to r, so that I get r squared over 2 minus 2 sine theta. This r squared becomes r cubed over 3 from 0 to 1. Okay, so when I plug in 1, I have 1/2 plus minus 2/3 sine theta. And when I plug in 0, I get 0, 0. Okay, so now I can integrate with respect to theta. I get 1/2 theta. Integral of sine is negative cosine plus 2/3 cosine theta from 0 to 2 pi. Or I mean the integral of negative sine is cosine. All right, and so I plug in 2 pi. I get pi plus cosine of 2 pi is 1, right? So I have that minus what happens when I plug in 0. 0 plus cosine of 2/3 is 1 again, or cosine of 0 is 1 again. So in total, I get pi. This 2/3 minus 2/3 cancels out. And my circle is going counterclockwise, so I could just keep my answer as pi. if my circle was going clockwise, so the opposite direction, I would just say like clockwise and put it like say that it's negative pi instead. Questions on part A? Does this mean whenever we say an integral of an enclosed region, we should think of using Green's theorem first before parameterization method? I feel like especially if you see it's like a circle in a 2D region, probably Green's theorem. Yeah. Like and also on the quiz, like some of them were like squares. And it was like they gave you each of the segments. That's also a clue that you should use Green's theorem because otherwise you would have to parameterize it 4 separate times. Like you would have to do the integral over this line, plus the integral over this line, plus integral over this line, and so on. And that's a lot of work. Okay. When would the work be 0 since it's a closed path? The work would be 0 if your field is a gradient 1 form. So if your field is a gradient 1 form from the independence of path theorem, if your field is gradient, then you would find the potential function and you do f of the endpoint minus f of the starting point. And so if it's like a loop, then your endpoint is probably going to should equal your start point. So you get 0. But in general, work doesn't give you 0 in general, even if it's a closed path. Like see how Green's theorem, it was a closed path, but the answer wasn't 0. Okay. Part B says what is the flux across the path? All right, so what is the definition of flux? So there was a Green's theorem version of flux, but say I like didn't remember what the Green's theorem for flux was, but you should remember what flux itself is. What is flux defined as? So whereas work, we saw that if our field, remember I'm calling my field to have components m and n. So work was just the dot product of like the first component dx, second component dy. Flux kind of switches them and there's like a negative sign somewhere. Flux is equal to m dy minus n dx. And keep in mind, my field is still mn. So like the components never change. Whatever is the first component is still m. So flux just takes that first component and gives it dy. And it takes that second component and it gives it negative dx. This is the definition of flux. Let me rewrite it so that like the dx is first. Okay, so I didn't change anything, I just reordered it. What does Green's theorem say? Green's theorem says that this is equivalent to the double integral of the partial of my second, like the whatever's in front of the dy, whatever's in front of dy with respect to dx, minus whatever's in front of the dx term, which is negative n. Take the partial with respect to y. That's what Green's theorem says. And so we get the double integral of partial mx plus n with respect to y. And if you look at my notes from this Green's theorem week, you'll see that the Green's theorem version of flux, it says exactly this. It says this equals this. All right. So what is the partial of m with respect to x? What is our field? This with respect to x, there's no x term, so that's 0. Here, what's the y term? There's a 2y, so the partial with respect to y is 2. So I get 0 plus 2 dx dy. I'll just put a dx dy here too. All right, and I have a circle, so actually, I don't even have to worry about the bounds because what is this? This is 2 dx dy. I can bring the 2 out so that it's a double integral of 1 dx dy. Recognize that a double integral of 1 dx dy is the area of your region. So 2 times the area of our region. We have a circle, a unit circle, which has an area of pi r squared. So it's pi, our radius is 1 squared. So final answer is 2 pi. Okay. And part C is F a gradient field? Explain why or why not. So in order to see if something is a gradient field, So right now, we're given, this is our function given in the problem. What does it say? X plus 2y. 2y, j. Okay, this is our field. In order to see if something is a gradient one form or a gradient field, you have to use the component test, or what I call the component test, which means you have to check like all the pairwise partials and see if they're equal. Now here we only have like two components, which I called m and n. So what do I have to check? I have to check that the partial of m with respect to y equals n with respect to x. So I kind of remember it as like first component over second variable, second component, first variable. If I had another component, then you have to check like all the other ones, like n with respect to z equals, say at my third one I called p. First with respect to third equals third with respect to first, and this one as well. But right now we only have two components, so this is all we have to check. And is this true? Well, the partial with respect to y of the first thing is 2y. The partial of the second thing with respect to x is 1. These are not equivalent, so we don't have a gradient field, not a gradient field. Okay, questions on problem 1. And I'll note that if you had like 3 components, like this has to be equivalent, this has to be equivalent, and this has to be equivalent. But like this doesn't have to equal, like these numbers don't have to equal these numbers. Just they're like separate. You just need this equality, and this equality. And if just one of them is not equal, then it's not gradient field. Okay. If other questions pop up, just ask them in the chat. I will be monitoring that. Let's go to question 2. Question 2, we're given this f function, and we also have this g function, and it says compute the derivative of f of g at the origin. All right, so what is it asking us? They want the derivative of the composition. So they want d of the composition. And they specifically say at the origin. So I know that I should evaluate it at 0, 0. How do we do this? Well, chain rule, right? Chain rule says this is equivalent to df evaluated at g of 0, 0 times dg of 0, 0. Okay, what is df? df, let's first look at some, like, let's first make sure we get the size correct. F has 3 inputs. F has 3 inputs and 2 outputs. So what should my derivative matrix size be? It should be a 2 by 3 matrix. 2 by 3 matrix. Okay, so let's specifically, what are they? The first, remember the outputs are the rows, inputs are the columns. All right, so the first output with respect to u, the derivative, it is 4u. Then the partial with respect to b is -1. Partial with respect to w is 3. All right, now I look at my second output. What is the partial with respect to u? That's 4v. Yep. And what's the partial with respect to b? We have 4u minus 5w. 4u minus 5w. Partial with respect to w is -5v. And I need to evaluate that at g of 0, 0. What is g of 0, 0? Well, they gave us the function g, so we can use that to find g of 0, 0. I'm just going to evaluate x is 0 and y is 0 everywhere and see what I get. So here I get e of 0 minus 0, 0 minus 0, e to the 0 minus cosine of 0. Okay, so what is that? Don't forget e to the 0 is actually 1, not e to 0. Okay, 0, and then 1 minus cosine of 0 is 1. So this is actually 0. So I just plugged in my 0, 0, and I got that g of 0, 0 is 1, 0, 0. Okay, and I also know that's correct. You can kind of do a self-check because I should have 3 components here. Why? Because I have 3 variables in my derivative matrix. So I like need 3 numbers to plug in. So it's a good thing that this is 1, 0, 0 and not just 0, 0. All right. Then what is the G? G has 2 inputs and 3 outputs. So I should have a 3 by 2 matrix. All right. So I look at my first output, the partial with respect to x. What is that? That's e to the x minus y. Partial with respect to y, chain rule. You need that like negative sign to go down. Negative e to the x minus y. All right, partial with respect to x is 5, and then y is negative 6y. Here we get sine x, and this is 2e to 2y because of chain rule. Or is it called chain? I think it's called chain rule. And then evaluate at the origin. Okay, so we start evaluating stuff. This is 4, negative 1, 3, 0. 4 minus 5 is negative 1, is 4 minus 0, sorry. It's 4, 0. Here I have 1, negative 1, 5, 0. Sine of 0 is 0, and 2. So when I do this matrix multiplication, I get negative 1, 2, 20, 0. Okay, what about part B? They say if again at the origin, all the inputs of f and g are increasing at a unit rate, at what rates are the outputs changing? So we see like this, like rates of changing, rates of outputs, and we're given some rates of inputs. You want to think ax equals b problem again from yesterday. All right, so in general, the outputs rate of change are equal to the derivative matrix times the input rate of changes. And they're telling us that all the inputs are increasing at unit rate, unit meaning 1. So I take the derivative matrix I found in part A, and I'm multiplying by 1, 1. All the inputs are changing at 1, 1. So I do this matrix multiplication, and I get 1, 20. So my first output is changing at a rate of a unit rate. My second output is changing at a rate of 20, whatever units they want. Okay, questions on problem 2. Can you use the inverse function theorem here to invert the function? I'm confused generally on what to plug in for each side of the equation. If you wanted to invert the function, yes. So let's say they want you to find the inverse of, let's say the question was find inverse of, of f of g. Or let's find like the derivative of it. Find inverse of the derivative. Or they would say like find derivative of inverse of f of g. Okay, that's better. All right, if you want to find the derivative of the inverse, what does that mean? I want to find the derivative of the inverse of f. This is what I want to find. So like they want you to do the inverse first and then take the derivative. But that's too hard to do. Like you don't want to do this composition and take an inverse and then take the derivative. Instead, the inverse function theorem says, as long as the derivative of f of g is invertible, as long as the derivative of f of g is invertible, which we can check because we know how to see if a matrix is invertible. As long as that's true, we can write this equality. We can instead just do the derivative first and then take the inverse. So I can take that derivative matrix I found in the beginning in part A and take the inverse of it, which you can use your normal 2 by 2 matrix rules for how to take the inverse. Okay, so we could have used the inverse function theorem to find the derivative of the inverse of g, because since the derivative of the composition is invertible, inverse function theorem gives us this equality, and we can take that derivative matrix from part A and just take its inverse. If the matrix hypothetically variables, what would we plug in there? If like if the input variables weren't all changing at unit rate,
No, like the inverse matrix.
inverse matrix.
Like if we had variables in there, would we plug in, because we're given like 2 points, 1, 0, 0, and 0, 0.
If the matrix. So like you would just do this whole process. It's still the same process. You still do this. You plug in 0, 0, and 1, 0, 0, and you get this matrix, and then you invert it. So like when you're finding the derivative of the inverse, you don't have to worry about like the input stuff.
Oh,
Hypothetically.
I see. Because we already plugged it in previous. Okay,
Yeah. We just handle it the normal case. And then do this extra step.
thank you.
Can you explain again why we would multiply the derivative matrix by the unit rate to find the rate? Yes, because in part B it says all the inputs are increasing at unit rate. So if all the inputs are increasing at unit rate, unit meaning 1, that means that my inputs are all 1. If they told me my first input is changing at a rate of 3 and my second input is changing at a rate of 2, then I would write 3, 2 and do that matrix multiplication and get different numbers. Okay, other questions? All right, let's go to question 3. It says, consider the following matrix A and a vector B. Solve the system AX equals B for the vector X. All right, this is our infamous AX equals B question, right? So we have AX equals B. In other words, that 4x4 matrix times X, where they tell us X is like star, 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 star. Let me just call them like X1, X2, X3, X4. Equals our B vector, 9, 6, 10, 2, given in the problem. Okay, how do we solve this? Well, one way is that you could do X equals A inverse B. But this is a 4x4 matrix. Like, I don't want to find the inverse of that. That's more work. I mean, you could. How would you do it? You would write A on the left and write the identity matrix, a 4x4 identity matrix on the right-hand side. Do a bunch of row reductions until you get the identity on the left side. Whatever's left on your right side is your inverse. And you could do that. Let's not do that. Let's do the row like augmented matrix way and row reduce. So I'm going to make a big augmented matrix. So I have my matrix A here on the left. And I have that dotted line thing. And I have my B vector. Okay, and now my goal is to try to row reduce till I get like an upper triangular matrix, ideally. All right, what do I need? Well, actually, I'm almost at the upper triangular point. I just need to get rid of this 3. So let's do row 2 is row 2 minus 3 of row 1. So I always kind of like use the row above it to try to get rid of whatever number I want to get rid of. So the first row stays the same. The second row is now 0. Negative 1 minus 6 is negative 7. 0 minus 9 is negative 9. And negative 2 plus 24 is 22. 6 minus 27 is negative 21. And the other rows are the same. Okay, so I could keep row reducing if I wanted to like get a diagonal matrix, and they'll tell me exactly my answer, or I can just stop here and start back substituting. So back substituting meaning I'm going to look at the last row, and remember that like my variables, how are things being multiplied, right? Like what would the last row be? Like how do you get this last number 2? You do the last row dot product with this vector to get 2. So that means that like what do we have here? 0 of x1 plus 0 x2 plus 0 x3 plus 2 x4 equals 2. So to myself, I'm always imagining like what this matrix multiplication is. That way I make sure I'm doing the correct variables, multiplying by the correct like coefficients. All right, 2x4 equals 2. So x4 equals 1. Then this row tells me x3 plus 6x4 equals 10. I just found out that x4 is equal to 1, so I can plug that in. And I solve to get x3 equals 4. The second row, I have negative 7x2 minus 9x3 plus 22x4 equals negative 21. I just found out what x3 is. It's 4. And I know what x4 is. It was 1. And I can solve to get negative 7x2 equals, I'll just say x2 will equal 1. And then finally, the first row has x1 plus 2x2 plus 3x3 minus 8x4 equals 9. What was x2? It was 1. x3 was 4. x4 was 1. Simplify, you'll get x1 equals 3. So my answer of the vector, like the x1, let me write it as my answer of x1, x2, x3, x4, the inputs, they are equal to, remember, x1 is the first one. Even though we solved it last, it was like the first component of my input. x1 is 3, x2 is 1, 4, and 1. Okay, so that's why I kept track of like the variables, because you could have easily like written the opposite way and said, oh, it's 1, 4, 1, 3, and that would not be correct. Okay. Questions on part A? Okay, so that requires knowing you're solving an AX equals B problem, row reducing, back substitute answer. Random question, is the exam going to be multiple choice? I believe it's going to be a mix of stuff, kind of like the previous Friday quizzes, like maybe some, like how the Friday quizzes always have maybe some multiple choice, like a fill in the blank or open-ended response. So it should be a mix of those. I think they also said that in the discussion page. Okay. Part B, compute the determinant of A and write your answer below. Perfect. Compute the determinant. Well, let's look at what did I do in part A. I'm just going to recopy what I did in part A. I took my original matrix. And now because we're just doing the determinant, we don't need that like B vector. So I just need my 4x4 matrix. What did I do? I did this combination, and now I have a reduced matrix. So this was matrix A. This is my reduced matrix. I'll call it R. And what do I do to find the determinant of A? The determinant of A is equal to the determinant of my reduced matrix divided by whatever row operations I did. What is the determinant of the reduced matrix? Well, it's super nice for us because it's an upper triangular matrix. So the determinant is just multiplying all the diagonal terms. 1, negative 7, 1, and 2. What row operations did I do? I just did a combination. And remember, combination does not affect the determinant. So just a 1. So my answer is negative 14. That's the determinant of A. Hypothetically, how would we find the determinant using the blocks in the matrix previously given? Let me see. I wouldn't use the block matrix. U is what row operations did you do? So if you do, so if you did a combination, you multiply by, like you have a negative 1. If you did a flip, like you flip rows, you have a negative 1. And if you rescale, that means like you multiplied by some k, right? Some constant k. So if I rescaled my whole row by 1/2, I would put a 1/2 here. If I rescaled my whole row by negative 500, I would put a negative 500 in the denominator. But yeah, if you're given block matrices, I would only use the like trick for block matrices if all the other numbers are 0, besides the ones on the block. Do we need to include multiplying by -3 as one of our row operations? -3. No, we do not, because the row operation we did is row 2 equals row 2, so that row stayed the same. And then I did like a combination of a different row. So in total, this is called a combination. If the row I'm looking at, like say I did row 2, I'm looking at row 2, and I did 1/3 of row 2, then I'm actually changing the row that I'm looking at. So that would be a rescaling. So if I do any change to the row I'm looking at, that affects stuff. Yep. And what I was saying yesterday about the row operations is that sometimes people do two things together and they say, oh, row 2 is going to be 1/3 of row 2 minus 3 row 1. And they call that a combination. That's not a combination because you changed the row that you were looking at. You did 1/3 of it. So really what you did was you rescaled by 1/3 and then you did a combination. So you did like two elementary operations together.
So the only thing that can be scaled in the combo without changing things is the one that we're not looking at. So like
Yes.
R1. Okay.
Yep, exactly.
I had a question. What if they're different row operations? Like you did maybe 3 or 4 different row operations. What would you do in that case?
If you did 4 different, yeah, so like say I have a matrix and I do row 1 is 2 row 1 and I get something. Say I then did row 3 is row 3 plus 2 row 1. Okay. And I get something. And then say I do another thing. Let's say I do row 5 is negative row 5 and I get a matrix. And let's say I do one more, right? Like row 4 equals 1/3 row 4 and I get something. Okay, so this is my matrix A, this is my matrix R. Determinative A equals determinative R over what row operations I did. Determinative R, it should be like some upper triangular or lower triangular or diagonal matrix because that makes the determinant easy to calculate because it's just multiplying the diagonal terms. So I get whatever that determinant is. What row operations did I did? Here I did a rescaling by 1/3. I want to put 1/3 here. Here I did a flip. Flip affects the determinant by -1. Here I did a combination that affects the determinant not by nothing. And here I did a rescaling by 2. So I should put a 2 in my denominator. Was that your question?
Yeah, I got it. Thanks.
Okay. Oh yeah, multiple row. Yeah, so you look at like each elementary row operation and what did you all do? Wouldn't you have to rescale the entire matrix, not just one row? Why would you have to rescale the entire matrix? I mean, you could if you wanted to get like ones on the diagonal, but you don't have to. Sometimes people, I guess like the question is like, what's the purpose of rescaling, I guess? It's that, like, say I wanted to get rid of this 7 here. Well, I don't really want to deal with a bunch of fractions, so I might say, oh, I'll do row 2 equals 1/7 of row 2. That way I can get like an identity on there. And then if I wanted to like get rid of this 1, then I can say I'll do row 2 equals row 2, or okay, it doesn't work in this example. Say there was a 1 here. Then I could do row 2 equals row 2 minus row 3. And you see how 1 minus 1 equals 0. So it would become 0 and the other number and the other number. That's why sometimes people do rescaling because we don't like fractions. Rescaling will come in more handy in Math 2400, where you have to get your matrix into something called a reduced echelon form, REF. And that requires, or like, I forget if it's RF or RREF, that requires ones on the diagonal. But you don't have to worry about that for this class. To clarify super quick, if we rescale within a combination, we don't do anything to the denominator. If you rescale within a combination, meaning my combination, like the row I'm looking at didn't change, but I could add whatever I wanted to. And yes, that doesn't affect anything to the denominator. So this could be -5 of row 4. It could be +10 of row 1, whatever. This is called a combination because I didn't change the row I'm looking at. Because row 3 equals row 3, extra stuff. Whereas here, see row 4, the row I'm looking at, I changed things to it. I multiplied by 1/3. So that would be a rescaling. Okay. So as a summary, right? 3 row operations, combo doesn't do anything, flip does -1, rescaling does K. So like doing this rescaling, it multiplies the determinant by 2. So this matrix determinant is double of what it was for A. So if I want to get back, I have to divide by whatever I did. Like if this is double, then I have to divide by 2 to get back A. That's why we're dividing by whatever we did.
Does anything happen when you like switch two rows?
Oh yeah, when you switch 2 rows, I didn't have an example there. Let's say I do one more row operation. Switching multiplies by -1. Let's say I did row 2 switch with row 3, and I get something. Then this multiplies by -1. Okay, let me do like a small example so everyone understands a little bit. Let's say I have an identity matrix, and I did, is the common, I feel like people are always confused with the rescaling. But let's say I do like a half of row 1, right? So I get a half 0, 0, 1. This is my side example. What is this determinant? The determinant of R here equals a half. So see, and the determinant of my original matrix, A, it was 1. Right? So by rescaling the first row by half, notice how it multiplied the determinant by half as well. In most cases, though, we don't know what this determinant is. That's what we're trying to figure out. So the determinant of A would equal determinant of R over what row operations I did. The determinant of R here is a half. And what row operations did I do? I multiplied by a half. So I should divide by that change I did and see that I get 1, which is correct. The determinant of the original thing was 1. So if you want to test out with the combination too and see why that works, you could just do a smaller example with the identity matrix, and you'll see no change happens. Okay. Other questions? All right, let's move on to question 4. Consider the parameterized curves in 3D. We have this curve and this curve. Compute the derivatives of these paths as velocity vectors. Okay, so all they tell me is just to compute the derivative. So let's do that. The derivative of the first path is chain rule 2 cosine of 2t, 2t plus 2, and the derivative of natural log is going to be the chain rule derivative of the inner thing, which is -1, over the actual thing, 1 minus t. All right, and what about the second thing? Derivative of the second curve is going to be chain rule -2 of t minus 1 times 1, 2, and e to the t. So I'm taking the derivative with respect to t, the variable I have. All right. Part B says these curves intersect at the origin when t equals 0. Using part A, compute the angle at which they intersect at the origin and write in your perhaps messy answers below. So we have these two curves. Let's call this gamma 1. This is gamma 2. And they're telling me they intersect at the origin when t equals 0. And they want us to find what is the angle between them. What is this orange thing? Well, first of all, you want to think like you have these two curly curves. You can't, like, how are you supposed to find the angle between two curly things? You can't. We need like vectors, straight vectors. So in order to find the angle at which these curves intersect, well, I need like some straight vector here that comes from gamma 2. And I need some vector here that comes from gamma 1. How do I get these vectors? Like, these are kind of like tangent vectors because they like barely touch my curve. And the tangent vectors are found by taking the derivative of gamma, taking the derivative of the curve. So if I take the derivative of gamma 1, I get this green vector. I take the derivative of gamma 2, and I get this purple vector. And actually, I found those derivatives in part A. And now I have two vectors. What's the formula for an angle between two vectors? It's u dot v over the lengths. Okay. But my derivatives have like variables in them. How do I get actual numbers? Well, they tell me that they intersect at the origin. So I can plug in t equals 0 and see what I get. This vector is 2, 2, negative 1. Let me actually follow my color scheme. Okay, and if I plug in 0 here, what do I get? I get 2, 2, 1. So when I want to find the angle between them, it's going to be arc cosine of 2, 2, negative 1 dot with 2, 2, 1, all divided by the length of u and the length of v. So what is that? That's arc cosine of, when I do a dot product, 2 plus 2 is, or 4 plus 4 is 8, minus 1 is 7. The length is square root of each component squared. So 2 squared plus 2 squared plus negative 1 squared. And this purple one is 2 squared plus 2 squared plus 1 squared. That's arc cosine of 7 over 4 plus 4 plus 1 is 9. Square root of 9 is 3. 3 times 3. So arc cosine of 7/9. And they told us to leave it in this like perhaps messy answer, so you don't have to evaluate that. Okay, and part C. If we use two independent parameters, t1 and t2, we could define a parametrized surface via this. Compute an implicit equation for a tangent plane to this surface at the origin. Okay, so let me actually move this down and so that we can see the problem. Part C. We have some surface. And my two curves, well, like, okay, I have my surface. And I want to find an implicit equation for a tangent plane to the surface. Think surface, tangent is always like barely touching it. So the tangent plane is going to be like this purple thing. Where it like touches the surface. Imagine surface, plane. Okay, I guess I could draw my surface a little bit better. All right. How do I get this equation of a plane? For any plane, I always need the normal vector. I need a normal vector that intersects where my plane intersects the surface. So that's a point. I need a normal vector. Well, I had my two curves, right? My two curves kind of like live on this surface. I had my like gamma 1 curve and my gamma 2 curve. And they told me it intersected at the origin. me draw origin. And with the two curves, I already found like vectors, tangent vectors living on the plane. My green vector lives on the plane, and my purple vector, oh, I used purple again, but purple vector also lives on the plane. So if I have two tangent vectors, how do I get the normal vector? Cross product. So my normal vector is going to be the cross product of the purple vector that I got from gamma 1 cross with the green vector that I got from gamma 1. I guess purple is from gamma 2. All right, so that means that it is the purple one, which was 2, 2, 1, cross with 2, 2, negative 1. If you do that cross product, you get 4, negative 4, 0. Okay, I can show the cross product just so everyone remembers how to do it. You always take the determinant of, you write ijk, ln your vector, vector. And you do a determinant. This is I times negative 2 minus 2, right? Minus j times, j uses these numbers. So negative 2 minus 2. And then k uses this, so plus k times 4 minus 4. So I get negative 4 I, wait, negative 2 minus 2. Negative 4i plus 4j plus 0k. Okay. Negative 4 and positive 4 here. And how do I write an implicit equation of a plane? Well, it's the normal vector dot with my variables minus some initial point. Remember that they said the curves intersected the origin. So my initial point I can use as the origin, goes 0. My normal vector is negative 4, 4, 0, 4, 4, 0. So this becomes negative 4x plus 4y plus 0z equals 0. Or just negative 4x plus 4y. Yeah. Okay. Questions on question 4. Why that specific order for the cross product? It didn't matter. You could have done the green cross the purple or purple cross green. You'll still get some vector. Like the only difference is you might get the vector that points down, but they're still like parallel. So they still count as like the normal vector. So you could have done purple cross green or green cross purple. You'll get like a scalar multiple of negative 4, 4, 0. And that's okay because like maybe the normal vector I get to be like negative 4, I got it as negative 4, 4, 0. Like I could have chosen the normal vector as negative 8, 8, 0. Like that works too. It's just a scalar multiple. They're all pointing in the same direction. Why is the x component of the gamma 2 derivative not positive 2t1? Because there was a negative sign here. So when you take the derivative, the 2 comes down. The 2 comes down and becomes 1. So it's negative 2t minus 1. That's using the chain rule. If that's a little confusing, you can also like FOIL this, I guess. T minus 1 squared is t squared minus 2t plus 1, which simplifies to the minus sign distributes. So you have negative t squared plus 2t, right? And when you take the derivative, what do you get? You get negative 2t plus 2, which is the same as writing negative 2t plus 1. Or minus 1. There. Okay. Other questions on question 4? Okay, let's go to question 5. Consider the vector field that, first of all, what is the divergence of F? So the divergence is defined as, let me call each of these components. This is my first component, second component, and my third component. The divergence is you take the partials of each component and you add them all up in their respective order. It's like the first one with respect to x, second with respect to y, third with respect to z. What do I get? Partial of this with respect to x is 3x squared. Partial of this with respect to y is 3y squared. And finally 3z squared. This is my divergence of F. Part B, compute the flux of F out of the sphere of radius 3 with outward pointing normals. The first thing I notice here is that they want a flux of F. If you see flux of F, usually signals divergence theorem or Gauss's theorem, Gauss/divergence. Another thing I see that is that I have a sphere. If I have a closed 3D thing, that's also usually a hint to use Gauss or divergence theorem. By the way, divergence and Gauss theorem is the same thing. I just use the words interchangeably. I forget what the videos uses. Maybe divergence. So divergence theorem then. Yeah, if I see a closed 3D thing like a sphere or a cube or a pyramid, maybe not pyramid. Pyramid might be hard, but like some nice 3D object, probably use divergence theorem. Usually if I see curl of flux, that means Stokes' theorem. Flux is just usually divergence. Okay, so if I want to compute the flux of F, what does the divergence theorem say? It says that the integral of some field ds equals the triple integral of the divergence of that field dv. Where this is over the boundary and this is over, I'll just write it like this is like boundary. Maybe I should write it cleaner. Boundary. And this is our like domain. Like i.e. whole shape. Meaning the whole sphere. Okay, what is the divergence of my field? Well, I just found the divergence of my field in part A. It was 3x squared plus 3y squared plus 3z squared dv. What do I do with these bounds, right? I have a sphere. I could keep things in Cartesian coordinates, but like, do you want to find what z equals to, like the square root of something to square root something, y equals square root something to square root something, and then evaluate all those square roots? No, we don't really want to do that. So instead, I'm going to convert to spherical coordinates because I have a sphere. Why does spherical coordinates work out nicely? Well, let me rewrite. This could be written as 3 times x squared plus y squared plus z squared dv. And in spherical coordinates, what is x squared plus y squared plus z squared? It's rho squared by the spherical conversions. So I have a triple integral of 3 rho squared. dv in spherical coordinates becomes rho squared sine phi d rho d phi d theta. What are my bounds? Well, I have a whole sphere, my whole sphere, like no restrictions at all. So what is rho? Rho goes from 0 to the radius of my sphere. What did they say? I have a sphere of radius 3. So it goes to 3. Phi, I have everything possible. So it's 0 to pi. Remember the phi bounds are like weird. It starts at 0 and the most it could be is pi. Since I have everything, it's 0 to pi. And theta is everything, 0 to 2 pi. Okay, I'll let you work out this integration, but the answer I get is 2916 over 5 pi. Questions so far? Okay, and part C, what is the flux of the curl of F across this same sphere? So let me rewrite out divergence theorem. Divergence theorem is, this tells me the flux of G, right? Because divergence, I told you that it's usually finding the flux of some vector field G. This is what divergence theorem says. Part C is asking for the flux of curl of F. So they are saying that we want the flux of, let me see, flux of curl of F. I'll just write the curl of F. Actually, let me write it in words. Curl of F. So they're saying that this G is now a curl of F. So what happens if I write curl of F using the divergence theorem? It says curl of F ds equals the triple integral of divergence of, my G is a curl of F dv. And what is this saying? This is saying to do the divergence curl of F. What is the divergence of curl? This is a fact that divergence of curl is 0. So we get 0 dv. So the answer is 0. So if you do a flux of curl of some vector field over 3D region, a 3D closed region, I should specify, you get 0. In general, flux of curl is not always 0. Like in general, if you see flux of curl, think to use Stokes' theorem. But because our object is a closed 3D thing, that means that we can use divergence theorem and simplify this way to get 0. Okay, questions on question 5? And remember, the facts are divergence of curl of F is 0, and the other one is like gradient of, or curl of gradient is whatever the other one is. Could you repeat, why is x squared plus y squared plus z squared equals rho squared? That's the spherical convergence. In spherical coordinates, rho is, I think it's square root of it. And then the other ones are the other, yeah. So that means rho squared is x squared plus y squared plus z squared. Could you repeat why divergence of curl equals 0? Yes, that's one of the rules to remember. Let's see, where's my little, I have a little chart. Here. Divergence of curl equals 0 and curl of gradient equals 0. So that's why divergence of curl equals 0. This is just a rule. Could you repeat why we took the divergence of the flux of curl for part C? Yes. So we have a closed 3D object, so that allows us to use divergence theorem, which is this. This is divergence theorem. Divergence theorem lets us find the flux of something, some vector field G. In this case, this G, we're letting it be the curl of another thing, curl of F. So if I plug in curl of F for this capital G, divergence theorem says curl of F equals the triple integral of, this triangle thing is still there because all I'm changing is this G. This G is now curl of F. And so I get the divergence of the curl of F, which is 0. In general, flex of curl of f is not always 0, because flex of curl of f, you usually use Stokes' theorem. And in Stokes' theorem, you don't always have a closed 3D thing. Like you could have a regular 3D object, like maybe a cap or like a non-filled in cone or something, and you would use Stokes' theorem, so you don't get 0. The only reason we get 0 here is because this sphere is closed. Closed is the important part. Stokes, you don't need a closed thing. It's usually like some surface or something living in 3D. Stokes has not closed shape. If you do Stokes for part C, would you still get 0? So Stokes' theorem, like you wouldn't usually use Stokes' theorem for a closed, like a sphere in this case. Like you need some, yeah, like it doesn't quite make as much sense in Stokes, I think. And if it's closed, the flex of curl will always be 0. Flex of curl. If it's a closed 3D object, like a sphere or a cube, then flex of curl should be 0. Okay. Let's see, back to this. All right, let's move on to question 6. Consider the following forms in 3D, alpha and beta here. Part A, of what vector field is alpha the work 1 form? So remember there was a quiz question on this also. Like part A was what is the work 1 form, and part B was what is the flex 1 form? Or flex 2 form? I forget what it was. Okay, of what vector field is alpha the work 1 form? Well, the work 1 form is written as like the first component dx plus second component dy plus third component dz. The associated field, this is work 1 form, is this. Associated field is F1, F2, F3. So the work 1 form of some field is F1 dx, F2 dy, F3 dz. And they wrote them exactly in that order, dx, dy, dz. So the vector field that's associated to it is xy, negative z squared, yz. This is the vector field that has this associated work 1 form. Oh, and using the IJK notation, you can just write it as IJK. Part B says compute and simplify d beta. So what is beta? Beta is z dx dy minus 3x dy dz. That's what beta says. And now I could take the derivative like term by term. So what is this expression? There's only a z in here. So I'm going to take the partial with respect to z, and I get 1 dz, and I wedge on the other stuff. So dx dy. What about over here? I only have an x term, so I'm going to take the partial with respect to x, and I get 3 dx, and wedge on the other stuff, dy dz. Now I have both things have are a 3 form, or 3 wedge thing, like 3 variables. So I need to like simplify further. How can I simplify further? Let's say I want to get everything in like x, y, z form. So let me change this. What is this equivalent to? If I move the x and the z term, a negative sign comes out. So negative 1 dx dz dy And then I want to switch the y and the z, so another negative sign comes out. So negative of negative, it goes back to positive, dx, dy, dz. So whenever you switch wedges, they have to be like next to each other. You can only switch adjacent wedges and a negative sign comes out. Like how I did here. I couldn't have just like swapped, I don't know, whatever swap I want. I have to do these two first and then these two. And that's why 1 of dz dx dy equals 1 dx dy dz. So I have 1 dx dy dz minus 3 dx dy dz. So that means I have negative 2 dx dy dz. Okay, and part C, compute and simplify alpha wedge beta. What is alpha? Alpha is xy dx minus z squared dy. So I'm just copying what alpha is, and I'm copying what beta is, that I can see it. Dy wedge dz. Okay. How do I like wedge things together? This is kind of like how you FOIL like polynomials. Like think of this as your polynomial and this as your other polynomial, and you're multiplying them. What do? You FOIL every single thing. So I'm going to multiply these x, y, z, and the wedges like stay in order. So this is dx, wedge the other stuff. Dx, wedge dy. And I have this term times this, which gives me negative 3x squared y dx wedge dy wedge dz. Then I have this middle term times this, so I get negative z cubed dy wedge dx wedge dy. And then this term, y plus 3xz squared dy wedge dy wedge dz. And then I have this term, which is yz squared dz dx dy. And this term, which is 3xyz dz dy dz. All right, and now a bunch of terms simplify. Right, what simplifies? If you have two variables that are the same in your wedge, it becomes 0. So this becomes 0, this becomes 0, this becomes 0. Anything else? Yeah, this also becomes 0. So we're only left with two terms, this term and this term. So I have the negative 3x squared y dx wedge dy wedge dz. And this purple term, let me also like change it so that it's in the form of dx dy wedge, like the correct order. So if I switch that, a negative sign comes out and I get dx wedge dz wedge dy. But then another negative sign comes out when I switch the y and the z. So it's still plus yz squared dx wedge dy wedge dz. So my final answer is negative 3x squared y plus yz squared dx dy wedge y dz. Question, do you have to do this step if we know, for example, that dx wedge dx is 0, or could we eliminate those and only skip to writing what remains? Like if you know they're 0 and you want to skip it, then maybe like write a side note like dx wedge dx, or like two things wedged together give you 0, something like that. In case like there's partial credit or something, but yeah, you could also just like not write these because it's a lot to write. All right, part D. What is the integral of beta over the unit disk in the xy plane? Write your answer below. Hint, do this directly, no theorems needed. Integral of beta over the unit disk. So I want to find an integral of beta. Beta here is this, the z dx dy minus 3x dy dz. And I'm doing it over what? A unit disk in the xy plane. So I'm in the xy plane and I have a unit disk. So this circle, unit disk, one with radius 1. So one way to do it is that I could keep everything in the forms language. So I'm going to keep all these wedges here. What do these wedges mean? dx dy, that's like the area projected to the xy plane. What is dy wedge dz? That's the area projected to the yz plane. Okay. So usually what I would do is I would like parameterize this circle, and I like plug in the parameterizations here, like whatever z is, whatever 3x is, and I take the derivative, and that's how I get like my wedge things. Now, since I'm only in the xy plane, it's a flat disk. What does that mean for z? If I'm only in the xy plane, that means z is nothing, like z is 0 always. This is my region that I have. I only have a unit disk in the xy plane, so z is 0. So when I plug in like a parameterization, whatever parameterization I choose, well, the z here, it would be 0 times whatever area projected to the xy plane, projected to xy plane. And then here I would have this like minus 3, whatever x is. I'll just put a dot here for now. But what is y dy wedge dz? That's the area projected to the yz plane. Well, I have no z at all. Like I only live in the flat xy plane. So if I try to project to a yz plane, nothing shows up. This is also 0. So I have an integral of 0 plus 0. So my answer is 0. That's all because I'm only living in the flat xy plane. So z is 0, and also there's no area in the yz plane. So the final answer is 0. No theorems needed. Question, when can you ignore the z direction? Oh yeah, I answered that. You can ignore the z direction because they told us we have no z. Our unit disk only lives in the xy plane. Okay, questions on this question? 6. Okay, let's do question 7. Question 7 says, consider the following joint probability density function, rho equals that, for random variables x and y on the quadrant in the plane given by that. For a chosen point at random with this density, what is the probability that x greater than 1, y greater than 1? Or greater than equal to, I mean. Okay, let me first draw like what this region is. They say we have 2 random variables, x and y. So I'm just going to draw the normal like xy plane, right? Xy. And we're only living in the quadrant where they're both greater. So we're only living over here. For a point chosen at random, what is the probability that x is greater than equal to 1? So I want to be greater than equal to 1. So I want to be over here. And y has to be greater than equal to 2. So I only want over here too. And both of those have to happen. Okay, so I wanted x greater than 1. I also want y greater than equal to 2. Where do both of those happen? Right here. The purple one. So the purple one is the only one we want to consider. So I want to find probability that x greater than 1 and y greater than equal to 2. What is that going to equal? Well, in probability form, like what is... Okay, just like how moment of inertia is the integral of the inertia element. Mass is the integral of the mass element. Area was integral of the area element. So here, probability is the integral of the probability element. Specifically, what is the probability element? It's whatever the probability density function is. And then d, whatever region we're living in. If we're in 2D, it's dA. If it's 3D, it's dV. So this is the probability density function. Not to be confused with when we're doing dm, the rho here is not a probability density function, it's just the density. The difference is that a probability density function, remember if you integrate it, it has to equal 1. a regular density can just be whatever it wants to be. All right, so we have integral of dp. So that means it's whatever the probability density is, which they told us is this 6e to the negative 2x minus 3y dA. Okay, and what are my bounds going to be? Well, the region, what region am I considering? I'm considering this purple region, where I can choose like dx dy, for example, if I wanted to, dx dy. So I draw a line in the increasing x direction. Where do I enter my purple space? I enter once x starts at 1. X equals 1. Where does my blue line exit? It keeps on going forever, right? I have no restrictions because x could be as big as it wants to be. We just need greater than 1. It goes to infinity. Out of all these blue lines I could draw, what is the smallest y value? Y is 2 at least, and it keeps on going to infinity. Okay, so now I have, let me get rid of, okay, this is the region. All right, so now I have this, and I could do a bunch of integration. So how do you do integrals with like the infinity stuff? I do the version where it becomes like a limit. So limit as b goes to infinity of 1 to b, 6e to negative 2x minus 3y dx dy. All right, so when I do the integral with respect to x, what happens? This becomes 6e to the negative 2x minus 3y over negative 2, right? Because I want to imagine when I take the derivative of this, a negative 2x comes down and cancels with this negative 2, and I'm left with the original function. Or you could have done like use substitution stuff. All right, so we have that where x goes to 1 to b, limit as b goes to infinity, dy. Okay, so what is this? This is the limit as b goes to infinity of, now I'm plugging b in whenever I see an x. I have 6e negative 2b minus 3y over negative 2 minus, when I plug in 1, I get negative 2 minus 3y over negative 2 dy. Okay. Let's see what happens. E to the negative power can always go to the denominator. So if you have something getting super large in the denominator, let me just write it out. 6 over negative 2e to the 2b plus 3y. If something goes really large to the denominator, the limit is 0. So I just have 0. And over here, this is just itself. So plus 3e to the negative 2 minus 3y dy. Okay, now we can integrate with respect to y. So I'm going to do the same thing or same technique of 3e to the negative 2 minus 3y dy. What happens when I integrate with respect to y? I have 3e to the negative this. And what comes out, like, what's in front of y? The negative 3. So I'm going to put that in the denominator. Because if I took the derivative of this, I get this. All right, from y equals 2 to b dy. So that means I have the limit as b goes to infinity of 3e to the negative 2 minus 3b over 3 minus 3e negative 2. When I plug in 2 for y, this is 6 minus 6 for negative 3. Okay, so again, this part goes to 0 because the e I could move to the denominator. This gets super large. Limit of a number over infinity is 0. 0. What about this term over here? I get positive e to the negative 8. Or in other words, 1 over e to the 8. Okay, so this was my final answer. Questions on part A? Okay. Okay, and part B, how would you compute the probability that x less than or less than 1? All right, so we're less than 1. Or y less than 2. Y less than 2. So our region is any of these, like anything in here. It could be less than 1 or less than 2, or it could also be both, right? You do not need to compute this, merely explain how you would do so. So let's set up what the integral would be. Or like how would we get this region? Well, think about this region. And this was from part A. This region that we're considering in red here is kind of like the whole thing, whatever we have, minus what we had in part A. Like the whole thing minus this purple stuff will give us what's remaining. So that's exactly how we're going to do part B. The probability of x less than 1 or y less than 2 is going to be, well, in general, what is the maximum, when you think of probability, like what's the biggest number you can have? Like 100%, right? 100%, or in other words, 1. So I have 1 minus the purple stuff, which was x greater than 1 and y greater than 2. Okay, questions on problem 7? Okay, question 8. Consider the unit density solid given by that. Part A, compute the z-coordinate of the centroid. All right, let's remember what the centroid formula is. It's z bar equals the triple integral of, you need z in the integrand, dB. And we're dealing with centroid. Yes, centroid. All right, and triple integral 1 dB. Let's see, centroid. Centroid was the one that did not have a mass in it. All right, centroid was just the integral. The integrand has that letter in it, ln dA or dV, depending on what dimension you're in. So it's just z dV over 1 dB. Okay. What am I integrating over? They tell me I have this unit density solid body given by this. What exactly is this shape? What does this look like? I don't know what it looks like, so let's just test points out, like, and see what it is. Let's see. Okay. If z equals 0, what does the equation say? It says x squared plus y squared less than or equal to 0. So that's just like a point. If z equals 4, say, what equation do I get? I get x squared plus y squared less than or equal to 4. So when z equals 4, let me pretend this is 4, that means that I have this filled in disk. I have a circle in the xy plane. When z equals 4, I have a circle of radius 2. What happens when z equals like 16? Well, then I have x squared plus y squared less than or equal to 16. So when z is 16, I have a circle of radius 4. So you see as z increases, each of these circles, each of these cutouts gets larger, bigger and bigger and bigger. And so this gives us this like paraboloid shape. Right, so this is what my shape looks like. And specifically, oh, they tell me that z goes from 0 to 4 only. So I went too far up. But, okay, let's pretend in my picture that this is 4 then. This is 2, 1, 3. All right, so this is my shape. Z goes from 0 to 4 only. Okay, so what are my bounds going to be? Well, I don't want to do things in Cartesian coordinates. The dV stuff, like I would have to find out. I mean, I could. But let's do a different coordinate system. Let's do cylindrical coordinates. In cylindrical coordinates, what happens to z? Z is still z, but the dv becomes r dz dr d theta. Now I have all of that divided by the triple integral of 1 r dz dr d theta. All right. What are my bounds? Z, I draw a line in the increasing Z direction. This orange line. Where do I enter? This orange line enters at the shape I have. The shape I have is the x squared plus y squared less than or equal to z, right? And in cylindrical coordinates, what is z squared plus y squared? That's r squared less than or equal to z. So in other words, z is always greater than r squared. So that's my lower bound. So I took the shape I'm entering and I rewrote it in cylindrical coordinates and try to get z to be something. That's always the technique you use. And then what is the upper bound for z? Where do I exit? Well, I exit out z equals 4. That's my upper bound. All right, so I have my z bounds. What is r? Well, r goes from, it starts at 0. And like, what is the radius if I draw a line radially outward? At most, it could be 4. Or what is like this point? When z equals 4, my circle has a radius of 2. So the radius is 2. Okay, maybe a better way of picturing it is what happens when I collapse to the z-axis. I get a circle of radius 2. Because at z equals 4, we have x squared plus y squared less than or equal to 4. All right, ln theta, no restrictions, so 0 to 2 pi. So 0 to 2, and all of these bounds are the same for the top and the bottom. Okay, and I'll let you calculate that, but I get this for the top and 8 pi for the bottom, for an answer of 8/3. All right, part B, write down the moment of inertia element for this body if it is rotated about the x-axis. So let me take my picture again. All right, part B, we're trying to find the moment of inertia element. What is the moment of inertia element? It's defined as r squared dm, where dm is the density dv. What is r in this case? The way you find r is you choose a random point on your shape. Let's choose this xyz point. And I want to find its distance to the axis we're rotating about. So we're rotating about the x-axis. So x-axis has the same x point and y z of zeros. So I'll label my axes also. This is x, y, z. Okay, and so I can just use the distance formula to find the distance between this point and this point. What does the distance formula say? It's x minus x squared plus y minus 0 squared plus z minus 0 squared, which gives me square root of y squared plus z squared. That means r squared is only y squared plus z squared. Density, they told me, did they tell you anything? They told me I have unit density. So density is 1 dv. So the moment of inertia element is just y squared plus z squared dz. Question in the chat, density P is not part of the centroid equation. Correct. Centroid does not have the density. Center of mass is the one that has the density part. Okay, questions on problem 8? Back to question 7. Does the or word in part B affect the region being considered for the probability in, as in part A? Yes, so this or in probability, it's like x could be so x less than 1, we get this yellow part, right? Y less than 2, we get this green part. And so the region we want to consider is this part, this, all of this part. Even though this intersects, we still want to consider it because in this part, x is less than 1, right? So it fits one of the conditions. So we still want to consider this highlighted part. Yeah. Then A was and then the and is more specific because both of these have to be satisfied together. So that's why it's only the purple part and it wasn't like this region for part A. Okay. All right. Final question, question 9. Your goal is to evaluate the following integral. And where the domain of integration D is the region in the positive quadrant of the UV plane given by this. Part A says, come up with a good coordinate transformation from UB to XY, which makes the domain into a rectangle in the XY plane, and write the coordinate transformation on your paper. So this is a change of variables question, right? Because they're telling you that you're in some coordinate world and you want to get a different coordinate world. So change of variables question. Okay, what is the goal of change of variables? It's that we want to find two nicer variables, which they're telling us to go to X and Y. They want some like X and Y world where X, the bounds will be between a number and a number, and Y will be between a number and a number. Well, they already gave us nicely some complicated thing between a number and a number. This is also another complicated thing between a number and a number. So why not, let's just call this X. X is going to be between 1 and 3. And let me just make this Y. So I'm choosing X to be V over U, and I chose Y to be UV. And the reason they say that this XY now makes a domain in the rectangle in the XY plane is because what do these bounds mean in the XY plane? If X is between 1 and 3, and Y is between 1 and 2, that region is exactly this rectangle. So that's why they say like this new transformation, this XY coordinate system, makes a rectangle in the XY plane. All right, so that was my transformation. Part B, it says use this to transform the area element, showing work on the paper. And they want us to write dx dy equals something. What does the change of variables theorem say? It says dx dy equals the absolute value of the determinant of this Jacobian of this derivative matrix, where x and y are the outputs and u and v are the inputs. Okay, so this du dv. So this notation is absolute value of, we need the derivative of the matrix, where the matrix has x and y as the outputs, right? So it looks like this, x and y, the outputs are the rows, and then the inputs are the columns, u and then v. Absolute value is important. We need a derivative of this matrix, where x and y are the outputs, u and v are the inputs. Okay, so let's find that. What is the partial of x? X is v over u. What's that partial with respect to u? Let me write it as v like this. Well, then I get negative v u to the negative 2. That's the partial with respect to u. What's the partial with respect to v? That's u to the negative 1. And then I look at y. What's the partial with respect to u? That's v. Partial with respect to v is u. So I have the absolute value of this determinant. What's the determinant? Well, it's negative v to the u negative 1 minus u negative 1v. So that's negative v over u minus v over u. So it's negative 2v over u. Absolute value. So when I take out like the absolute value, it's positive 2v over u. Therefore, dx dy equals 2v over u du dv. Okay. Part C says evaluate the integral, showing work on your paper and writing your answer. So the integral they want us to evaluate, they gave us at the very beginning. They want us to do double integral of u squared v squared. U squared v squared du dv. That's what they want us to find. as shown in the problem. Okay, how do I do change of variables? Also, let me write what my x and y were again. X was that and y was that. Okay, so change of variables, 3 parts you need to change. You need to change the differential. What is du dv? From part A, we know what dx dy is. So that means that we could get what du dv is. What is du dv? Du dv, I'm just gonna divide by 2v over u on both sides. So I get u over 2v over here, dx dy. So du dv is u over 2v dx dy. And for now, yeah, let me keep the u squared v squared here for now also, u squared v squared. So I have a double integral like that. What are my bounds? X is between, well, we found x is between 1 and 3, y is between 1 and 2. X is between 1 and 3, y is between 1 and 2. So now we have to worry about getting this integrand stuff all in only x's and y's. What can we do? Let's look a little bit. Notice that y is uv, so that means that u squared v squared, that could just be y squared. This part, that's y squared. What is u over v? Well, for x, I have v over u. So what if I just take the inverse of it, or like the reciprocal? Then 1 over x would be u over v, right? Which is what I have, u over v. So I want a 1 over x. And don't forget that I also have this a half here. This 1/2. 1/2. So in total, that means I have y equals 1 to 2, x equals 1 to 3 of y squared over 2x dx dy. And if you want to evaluate that, you get 7 natural log of 3 over 6. Oh wait, did they say to, yeah, they said to evaluate it. Yeah, so you'll have to evaluate it. But okay, so you see how sometimes I kind of like left this integrand here because sometimes things might be able to cancel out. Or if it works out nicely, you can find directly that like we saw here, this was y squared and this was 1 over x. But other times you might be able to like simplify more and see what happens. Okay, any questions on question 9? Okay, if no, then that's the end of the spring 2020 A practice exam session. Okay, let me stop the recording.